A fixed pitch propeller is one whose angles are set for good, designed in by an engineer. The length of the blade has a pitch to it in different locations. There are different angles. I hate to use the term pitch, but we call it a fixed pitch propeller, and that's a way of saying that this piece of aluminum is shaped forever, or ideally forever, barring wear and tear. And you can see on the what is the curved side, which is the blade back, that we have a different amount of curve and many different degrees as measured on the flat side, or the face, which faces the pilot. So as we draw nearer to the hub, the increased amount of material is angled differently than as we approach the tip, where the angle is thinner. Mind you, this one has been hit, so it's hard to tell. But nonetheless, you can tell that the thinness of the material changes towards the top, or the tip of the blade, and is much thicker and curved and has greater angle towards the hub or center. Okay, that's fixed for good. Again, barring any strange strikes and a good amount of wear and tear, which changes the blade greatly over a great amount of time. We can measure those changes, or actually the amount of angle on each station of the blade, because of course over the length of the blade, the amount of degrees that each station has is increased towards the hub and decreased towards the tip. We are looking at a representation of a cross section of a blade, and over here what we see again I've referred to as a chord line. It's that imaginary line traveling from leading edge to trailing edge, and if I were to take it and put it on the propeller as this represents its axis of rotation, that is the shaft to which the propeller is connected in its spinning thusly, and then of course that intersects another imaginary perpendicular line called the plane of rotation. It's perpendicular to the axis of rotation, and we use it simply to make a measurement. So typically what measurements we're going to look at is where this where this plane of rotation intersects the chord line, and what we end up here with is an acute angle in here, and that represents the number of degrees that this station is set at in perspective, or in a relationship to the plane of rotation here. So as we approach the hub of a propeller, then as you can see, the hub area has more material and has greater twist to it, and so we say that this has a greater angle, a blade angle, and that's what this is. It's the blade angle is this acute angle formed between the chord and the plane of rotation. So the blade angle then is greater towards the hub, but it changes as we move further and further up, or in this case up, but greater towards the tip. More towards the tip we move, the thinner the material is, and the flatter or more fine is the blade angle. And so what we'll see is that as we move further and further towards the tip, we'll see that the angle changes, that it becomes more fine right in here. So the blade angle changes as we move along and further out towards the tip of the propeller. And so this distribution of blade angles is what people call the pitch. What is the pitch of the blade? Well, it changes as we move further and further towards the tip. And as we move further in, it becomes more increased. And of course, as we move out, it becomes more thin or more fine. And that's the nomenclature of pitch, which is really just a distribution of pitches or of blade angles. How about that? Now, the terminology is there simply to say that the two lines intersect. And as I said, when we intersect these two lines, we end up with a, okay, so with a little bit of imagination, I think you could probably see that this would be about the tip, and of course, this is closer to the hub. A fixed pitch propeller is one whose angles are set for good, designed in by an engineer. The length of the blade has a pitch to it in different locations. There are different angles. I hate to use the term pitch, but we call it a fixed pitch propeller, and that's a way of saying that this piece of aluminum is shaped forever, or ideally forever, barring wear and tear. And you can see on the what is the curved side, which is the blade back, that we have a different amount of curve and many different degrees as measured on the flat side, or the face, which faces the pilot. So as we draw nearer to the hub, the increased amount of material is angled differently than as we approach the tip, where the angle is thinner. Mind you, this one has been hit, so it's hard to tell. But nonetheless, you can tell that the thinness of the material changes towards the top or the tip of the blade, and is much thicker and curved and has greater angle towards the hub or center. Okay, that's fixed for good. Again, barring any strange strikes and a good amount of wear and tear, which changes the blade greatly over a great amount of time. We can measure those changes, or actually the amount of angle on each station of the blade, because of course over the length of the blade, the amount of degrees that each station has is increased towards the hub and decreased towards the tip. So what we're saying then is that a fixed pitch propeller has a certain kind of efficiency in each of the different stations. Therefore, when they design, the engineers design a fixed pitch propeller, we are pretty much set in stone that efficiency, and that kind of propulsive efficiency is a sort of a compromise, because in certain conditions we could probably do a little better if we could just adjust, if we could simply adjust the blade angle in these different stations. How we overcome this fixed or fixedness of these propellers, of these fixed pitch propellers, is to come up with a better design, one in which we can adjust for these different conditions. We can adjust the blade angles as we're flying. And to do that, of course, we'll be talking about the propeller governor. But I do want to show you exactly what we're talking about. We're talking about a constant speed propeller, one which can adjust the blade angle as we are flying for different effects. And we just happen to have a little bit of one of these. It would be difficult to fly a plane and go out and change that blade angle, but instead what we have attached usually to the pad that is in front of the engine, the governor pad, we usually have a governor that is fixed into an accessory drive and also is available to oil. How about that? And this, of course, is a governor, and it uses the oil from the engine, which is usually about 90 psi, 60, 70, 80, 90 psi, and it takes it in, of course, and you can probably tell it has a spur gear pump. So in a way, this is a boost pump. A governor effectively is a boost pump for that oil, changing it from a simple 90 psi to about 180 or more. And so this typical cutaway view of a governor should also capture your attention. There's a spring, a speeder spring or a rack and speeder spring, which sits atop these flyweights, which are just not popping out real fast today, but sit inside of this cup. You can see these flyweights, maybe you can see their profile. I'll show you a little more closely in a minute. But the speeder spring rack, of course, is attached to something we have in a constant speed propeller cockpit, and that is in the middle of the throttle, the black knob and lever, and the red knob and lever. Right in the middle is typically a blue lever, and what that is called is, often it's called the propeller lever or the speed lever, and it controls effectively a constant speed prop. And so in the middle they have that control that's connected to this and drives through other connections. It is able to compress the tension on this group of springs and fight against the spinning motion, the centrifugal force of these spinning flyweights. And let me show you a little bit more about what we're talking about in better detail. Here, as I drop it, comes to you a cutaway view, again, of that area that we were talking about just a second here, talking about this, these flyweights, which you can probably see, and of course the shaft, which the pilot valve sits in. Okay, so what we have here sitting atop the toes of these flyweights is this pilot valve, which travels within this spinning shaft. And if you can probably tell, in a matter of minutes I'll be able to get this to illustrate for you even more detail, that this spins within the governor and directs oil through this spur gear pump into either the propeller or allows that oil to drain off and go back to the engine oil sump. I can probably get you an even better view of some of this. Again, here is here's that shaft, and you should probably see that on some of these shafts you have this pilot valve, a solid pilot valve for counterweighted gain, and what it does is it sits atop these fly weights, which, as you can see, if they are spinning, will sense centrifugal force and push up on the against the compression force that is sitting atop these pilot valve, okay? And so the pilot valve, though, you should probably could tell, has lands and, of course, permits ports, these ports to be direct oil or not. So as it moves up and down, it closes off or opens up the ports that are in this spinning shaft, and either allows the oil to go direct into the propeller or back to the engine sump. When the tension on the speeder spring is equal to the centrifugal force on the toes of the flyweights, they're said to be at equilibrium, or what we all call on speed. So in other words, the pilot has moved the blue lever in to such a position that the speed is desired, is met by the engine, and no need for any adjustment. So in a propeller, in a constant speed propeller, when the pilot has moved the speed lever, also known as the prop lever, when he has moved the prop lever to a spot and the speed that he desires is attained by the engine, and it just stays there, this equilibrium is called on speed. But if, for example, the pilot pushes the speed lever forward and compresses the spring on that pilot valve plunger, he's going to initially put the pilot valve plunger to push greater on the toes of the flyweight, tilting them into the letter U for underspeed. And when they reach underspeed, that's going to push the pilot valve plunger into such a position that the oil in a counterweighted prop, that's one with these weights attached to the propeller area, it's going to send oil at about 180 psi into a piston that pushes the blade to a lower blade angle. In other words, as a constant speed counterweighted propeller approaches too slow a speed, or an underspeed, the oil is going to be directed into the piston, into the propeller, and it's going to drive from high blade angle to lower blade angle. It's going to drive these blades to an angle that is lower, so it can catch up with the desired speed that the pilot has used the propeller lever to achieve. When the tension on the speeder spring and the when the tension on the Gradually, though, the speed that was desired by the pilot will be met by the engine, and then what happens is the tension on the spring equals the force of the flyweights within the governor, and what happens is they form a state of equilibrium we call on speed. Then no oil has to flow between these different parts of the system. So we're in a state of hydraulic lock. No oil need move because the pilot valve has been pushed into such a position of equilibrium where no oil is allowed to travel through the various ports. As you probably can see, it does not line up. The pilot valve plunger does not allow any oil to travel through that, it's in a state of steady state of hydraulic lock, and the blade angle is approaching a more thin or fine state, because it doesn't need to go as fast or any more quick, and it doesn't need to move any more slow. So it approaches a moderate location, which we can demonstrate with our own film in a minute. Now, if the pilot has moved the propeller lever or the speed lever aft, that is towards himself, then it will reduce the amount of tension on the speeder spring, and it's a way of saying or requesting a lower RPM. And so what happens then is the amount of centrifugal force in the flyweights push up against this reduced tension here, allowing the pilot valve to move up, and thus finding an opening here which allows the oil to travel back to the sump. When that happens, the counterweights on the propeller, the counterweights increase, or the force on them increases enough where the propeller the piston moves aft, and that increases the blade angle. When you increase the blade angle, you reduce the speed, and that's what we're after, because we're overspeeding. So when the pilot, or even natural circumstances such as a plane pitching down ever so slightly, when it moves downward, there's less strain on the engine, the speed starts to increase, and yet the prop lever may be set in one location, and the prop governor acts much like a transmission to sort of steady out the speed, and does this by increasing the blade angle. In the over speed condition, it increases blade angle here, and allows the increased blade angle slows down it slows down the RPMs of the engine. So it does this by utilizing ATM, and it overcomes the greater force we call CTM. CTM is centrifugal twisting moment, and centrifugal twisting moment is always greater than ATM, and the nature of CTM is that what we do, we use that to decrease blade angle, but ATM is the force that we use to increase blade angle, but we have to amplify it with these counterweights. That amplifies ATM, and that moment is then increased, and that increases blade angle, which slows down the RPMs, and that's why we're again naturally utilizing either CTM or ATM. CTM to decrease blade angle, ATM to increase blade angle. So what we're saying is we're using both ATM, aerodynamic twisting moment, and CTM, centrifugal twisting moment, these two ever-present, always present forces. We're utilizing them in a way that can change blade angle, that is used to change blade angle in addition to our other mechanical games that we play. For example, to increase ATM, to increase blade angle, we must amplify it. And to do that, we add weights, or what we call counterweights, to a propeller to amplify ATM and create greater moment to overcome CTM. So these two forces are utilized in conjunction with the force of oil that we use, the hydraulic force that oil imparts to a propeller. We can use in a counterweight propeller, we can add oil to reduce blade angle, That is, we start off with a higher blade angle with a counterweighted prop, and as we need to increase speed, we need to reduce blade angle. We'll send oil to the propeller piston. That will reduce the blade angle, increase the speed. And that would be in a case of an underspeed. But in the case of an overspeed, or where the flyweights in the governor, in the top of the governor, where the flyweights overcome the compression force of the spring, where that exists, we then need to increase blade angle and reduce the speed. Now, all of this is done dynamically. It's going on constantly with these propellers, because of course the governor is acting sort of like a transmission. So constant speed propellers are always able to make small adjustments based on the location of where that oil is being sent, either a little bit to the propeller or a little bit away into the sump. And of course this will change the blade angle a little bit less and a little bit more. And it does this constantly, and as the pilot moves a propeller lever, he or she is now setting a new RPM, and it more or less keeps that speed constant to wherever the pilot has set that. And that's the neat thing about using it with a counterweighted prop. But how do we use it with a non-counterweight? Well, very similarly. Again, underspeed and overspeed remain the same within the propeller governor. So the propeller governor isn't changed any, but the way it is used is changed radically. So its design is changed pretty intensely. Normally we have a solid pilot valve plunger, but in the case of a non-counterweighted propeller, we're going to need to make a different porting. The porting of the oil is quite a bit different, and so in those cases we'll probably run into something of a plunger, a pilot valve that is hollow, and it allows for different porting within the shaft, and that's the trick that is going on with these different pilot valves. I keep running into solid pilot valves, but I have a hollow for that typically runs with a non-counterweighted. But again, all that we're saying is that these counterweighted and non-counterweighted propellers work in pretty much opposite ways. As I've taught you pretty intensely now, and what we were reviewing is that the oil on a counterweighted prop is sent to the propeller in order to reduce blade angle, because a counterweighted propeller typically has a high blade angle it's set for normally, and then we reduce the blade angle by adding oil, and we reduce blade angle in order to increase speed. Conversely, of course, with that, we remove the oil and send it to the sump in order to get the counterweights on the propeller to overcome CTM, and the ATM is greater than, because it now has these weights that are amplified by moment. And so you have a certain amount of force to which it applies to these weights, and of course as a consequence what we have is an increasing of blade angle that will slow it down when it's in overspeed. And what happens is the flyweights in the top of this governor are now spinning too fast, and they've pushed the pilot valve plunger up and ported the oil away from the piston into the sump, and then of course the counterweights on the propeller pull the piston in and thus increase blade angle, which will slow down the propeller, or the engine I should say. And of course, as the speed slows down, the centrifugal force on the toes of the flyweight in the governor becomes a little less, and the toes of the flyweight are fighting to get in balance, I guess, with the compression force of that speeder spring. And so what we have are these opposing forces that are now coming to equilibrium, or what we call on speed.